The conformational stability of cyclic organic molecules. The stability of cyclic organic compounds was initially predicted by Adolf Bayer in 1885. Bayer believed that all cyclic compounds were planar and proposed that their stability could be determined by the difference between the ideal tetrahedral bond angle of 109.5 degrees and the actual bond angles in the planar cyclic structures. For example, in cyclopropane, the bond angles are 60 degrees, representing a 49.5 degree deviation from the ideal. Bayer argued this angle strain decreased cyclopropane's stability. Similarly, he predicted cyclobutane would be more stable than cyclopropane as its 90-degree bond angles deviated less from the ideal. Bayer also predicted cyclopentane would be the most stable cyclic compound as its 108 bond angles were closest to 109.5 degrees of the tetrahedral arrangement. He thought cyclohexane and larger rings would be progressively less stable. However, Bayer's predictions were largely incorrect. Contrary to his assumptions, most cyclic compounds were not planar, but instead adopt non-planar puckered conformations to minimize strain. For instance, both of these molecules, cyclobutane and as well as cyclopentane, they are going to twist out of a planar arrangement in order to minimize angle strain and number of eclipsed hydrogens. Going on to cyclohexane, cyclohexane is actually more stable than cyclopentane. And this is because of its ability to adopt a low strain chair conformation. So here is one of the chair conformation of cyclohexane, which is completely free from angle strain. Here the bond angles are 111 degrees and all adjacent bonds are staggered. So here are staggered hydrogens. And this can also be seen from the ball and stick model. This table right here shows the heats of formation and strain energies of various cycloalkanes. Now here, this column, which is the strainless heat of formation column, indicates the calculated heat of formation if the cycloalkane had no strain. But the actual heat of formation, which is this column, is higher. And the difference between these two is going to represent the strain energy. What we can see from the chart is as the ring size increases, the strain energy per CH2 group generally decreases. Cyclopropane has the highest strain at 9.1 kilocalories per mole per CH2, while larger rings like cyclohexane and cycloheptane have essentially zero strain or less strain. This tells us that larger cyclic compounds such as cyclohexane and cycloheptane are going to adopt conformation that will minimize angle strain, making them more stable than smaller, more rigid ring structures such as cyclopropane and cyclobutane.